Hello everyone, in this presentation I'll be talking about my analysis of raw wine data.txt. The aim of this analysis was to build an accurate model which can predict the quality of a wine based on the given input variables. In this analysis we are using aggregation functions. To add data to an aggregation function, it is important for us to transform that data. To study what transformation needs to be applied to each variable, we first need to study its individual data distribution. To do so, we built histograms for the different variables. As we can see from here, citric acid follows a linear relationship and is right skewed. Chlorides resemble a normal distribution and are heavily right skewed. Total sulfur dioxide resembles a normal distribution and is right skewed. pH resembles a normal distribution. Alcohol again resembles a normal distribution and is right skewed. Our output variable resembles a normal distribution. And also please note that the value of the different classes here is very imbalanced. By value, I mean the frequency of the different classes here is very imbalanced. After studying these distributions, we were tasked with selecting the four most appropriate input variables for our aggregation that need to be fit to our aggregation function. For that, we study the Pearson correlation between the input and the output variables. As can be seen from this table, pH has the lowest correlation with our output variable. So we'll be discarding this as the variable. So we will be discarding this variable from our aggregation function. After selecting the four most appropriate input variables, we need to perform transformations. We perform a polynomial transformation on citric acid as it was previously right skewed, and the p-value chosen is less than 1. For chlorides, we also perform a polynomial transformation, and since it was previously right skewed, we chose a p-value less than 1 to be 0.1. For total sulfur dioxide, we choose a negation transformation as it has a negative correlation with our output variable. Now, this enables a monotonic relationship between total sulfur dioxide and quality. Please note we did not use a negation transformation in case of chlorides because the extent of negative correlation was very low. Next, we again use a polynomial transformation with a p-value less than 1 for alcohol as it was previously right skewed. After performing these transformations, it is important for us to scale our data. Scaling our data helps us to better interpret the weights that we receive from our aggregation functions, and the weights we receive are more comparable. We fit our data on three aggregation functions, and the weights received for each of the input variables can be seen in this table. We also calculate the evaluation metrics for the different aggregation functions, which can be seen in this table. From the above table, we can see that weighted arithmetic mean is the best fitting function for the supply data as it has the lowest root mean square error, and it also has the highest Pearson and Spearman correlations. But please note that even though the correlations have the highest value in case of weighted arithmetic mean, they are still low. After selecting weighted arithmetic mean as our best fitting function, we use it to predict an unseen instance. The predicted quality of that instance is 5. That this is a reasonable result the because the level of alcohol is midway between the minimum and the maximum for alcohol, which is 8.3. So we also predicted that the quality of the wine should be somewhere between somewhere at 5. Also, since we're only using alcohol as the indicator because it has the highest correlation with our output variable, while the rest of the variables have a relatively low correlation. To talk about the ideal scenario, we would say we would get the best quality wine when citric acid lies between zero point 0.2 to zero point 0.8 as it has a very low correlation, but higher is better based on the weights we get from our fitting function. Then for chlorides, it can lie anywhere between 0.034 to zero point 0.2, but again higher is better because based on the weights we get from our aggregation or fit function. Then for total sulfur dioxide, it can lie anywhere from 6 to 75, but since the correlation is very low, but the lower values would be better based on the fitting function, based on the weights of the fitting function. And for alcohol, higher values would be better, as it has a strong positive correlation with our output variable and also based on the weight. To conclude, I'd like to say that the prepared models are not the best models to accurately predict the output variable, as we can, because of the Pearson and the Spearman correlation values that we get. And we need better input variables, which can be seen from the correlations we get on the different variables with the output variable. The these this poor performance can be also be attributed to the fact that the distribution of the data that we get in our subset is very unbalanced in terms of the output variables. So our data is not able to accurately sorry so our model is not able to accurately get insights or learn patterns for the different classes.